Double word.
All right, morning everyone.
Good morning.
So we're gonna finish up talking about compiling classes and objects kind of stuff. And that's gonna finish up our talking about compilers. I feel a little conflicted about this because like everything else that we've talked about so far is pretty much going to be required for any computer that you build and any language that you build or whatever. Does your language have to be object-oriented though? No, it doesn't. So this part feels a little kind of irrelevant, also because I just don't like object-oriented programming, but that's just me.
I wonder what gives that.
No, I mean, it's not just me. I'm objectively correct, but
Is that why you teach functional programming?
I teach functional programming because I like functional programming, but which is also why I don't like object-oriented. But whatever. No, a lot of the languages that you've seen are object-oriented, and so it makes sense, and it's great to see how they actually work. So I don't have a problem with that. All right. So last time, I just want to recall what we were talking about last time. So we looked at this simple main class that is the main function that all it does is create a square game object and then call some methods on it, right? We will get into today talking about like how does that actually work to create a new square game object, but the one thing that we did talk about is how it works when you say do game.run, right? So because this is not a class, if you have the name of a class dot a method, then it just means you're calling a function in that class, and you can just translate it directly to a call. But since we have an object dot run, we can't just say call game.run. And so, right, we talked about how, and this is really the way that all object-oriented languages work, is that the object on which you're calling a method really is just an argument to the method, right? So when you call the method, it's like, well, I'm going to run some code, and I have to know what object it is that I'm supposed to be running on, and so that's just an argument. In Java, it's called this. In Python, in Java, it's called this, and it's kind of magically provided to you. In Python, it's called self, and it's not quite so magic because you have to actually write the fact that it has this self parameter, but it's the same thing that's happening. And so Jack is more like Java in the fact that it's, to a Jack programmer, it's magic, right? They never have to write this argument. But when we're compiling it, obviously we have to take that into account. So the way we actually compile this game.run is we first, wherever the game variable is, we first push that on the stack, and then we call square game.run. And of course, here we say it has one argument, even though it looks like it has 0. And if there were arguments here, of course, we would just first push game on the stack and then push the rest of the arguments. And then we would just add, however many arguments it has, we just add 1. And that's the number that we put when we call it. So a couple questions for you. Number 1. So when we parse this, do game.run, right? All it looks like is, well, we have do, and then we have an identifier and a dot and another identifier and some parentheses, right? How can I actually tell the difference between something where I'm calling a function of a class, like, saying, is there an example up here? Maybe not this one. Like when I say, output.println, right? That's calling the println function in the output class, versus calling a method on an object. How can I tell the difference when I'm compiling it? Any ideas? So in other words, let me just...
Game is a variable name?
hang on one second. So if we see, identifier dot identifier, you know, blah, 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 how can we tell whether, really, this is identifier one is the name of a class or an object. So what were you saying, Daniel?
If the thing before the dot is in the symbol table, it is an object. If it is not, it is a class.
Right, exactly right. Yeah, so we just try looking up this identifier in the symbol table, and if it's there, that means it's the name of a variable, hence it's something that's holding an object, and we're calling a method on that object. If it's not in the symbol table, that means it must be the name of a class. Well, or it means that someone misspelled a variable name, right? So in a real compiler, you could also store names of classes in the symbol table and just say that they're a class, and then you could look it up and say, oh, if it has to be there, and if it's there, I can tell what kind of thing it is. And if it's not there, then it's an error, and I can say, you misspelled something, or I don't know what this is, right? But yes, for the purposes of this project, you can just say, assume that anything in the symbol table is a variable, hence an object, and anything that's not is must be the name of the class. So answer, look up identifier one in the symbol table. If it's there, it's a variable, and hence holds an object. Otherwise, it must be the name of a class. You could also imagine some languages make the choice that, for example, you could say all class names are required to start with a capital letter and all variable names are required to start with a lowercase letter. There's some languages that make that choice, and then you can actually tell just from the syntax. You can parse them as different things because they just have to start with different letters. Java and Jack do not make that requirement, right? We often write code that way just as a convention, that we name classes with uppercase letters and we name variables with lowercase letters, but the language doesn't require you to do that. It's just a social convention. Because it's still useful as humans to be able to parse it and be like, oh, this must be the name of a class because it starts with an uppercase letter. You don't have to keep a symbol table in your head to read it. So. Okay, here's the other question. When I see game.run, right, how do I know to say square game.run? Zach?
You have to know the type of the object.
Right, and how do I find out the type of the object?
The declaration.
It's in the symbol table.
Right, it's in the symbol table too. Right, and this is why we need the types of variables in the symbol table. This is the only reason, I think, in this language. In other languages there might be other reasons, but the important reason that we need to know the type of a variable is that if it's an object of some class, we have to know what class it is so that we know, which methods to call on that object. So, and then, well, this is like a Q&A. This is like the frequently asked questions section. Question, how do we know to translate, e.g. game.run into square game.run? And the answer is we look at the type of the variable game, which is stored in the symbol table. Okay. Any questions about that? Obviously, also, when we said push local 0, how did we know to say local 0? Well, that's also in the symbol table, right? We looked up game and we said, it's a local variable, it's local variable number 0, so I need to say push local 0. And if it was, if it was an argument, we could say push argument 3 or whatever. Okay. Well, let's now look at square game. Great. So this this one that we just looked at, sorry, going back to this. It had some interesting code in terms of calling, methods. But as a class itself, it's not very interesting because all it has is a single function, and we already know how to do those, right? So now I want to look at square game, which is actually interesting as a class because it's got some fields, it's got a constructor, it's got some methods, right? And so we're going to need to talk about all those things, how we actually deal with those things. So if I go over to, let's think about this in terms of the syntax again. So a class, right, starts with the keyword class, name of the class, and some class variable declarations. And I think, actually, I don't think we wrote the syntax for class vardec in here yet. So let's write that down just so we know what we're dealing with. So a class vardec is, what is it? Well, it's either the keyword static or the keyword field, followed by a type, followed by some variable names, and then optionally we could have more variable names, and then a semicolon. Okay. So actually nothing too difficult here to deal with. Right, when you start parsing a class, you peek at that first token and you see, okay, if it's static or field, then I know I'm parsing a variable declaration. And if it's, well, what would it be? If it's a subroutine declaration, then it's going to start with either constructor, function, or method. So that's pretty easy to tell those apart. Then you just read in the type, and then you can read a bunch of variable names with commas, and they all have that same type. Let's see, what else do we need to talk about? I guess we already, we have only talked about functions so far, but we're going to have, now we'll have to deal with constructors and methods. And you shouldn't need, well, there's different ways you could do this, right? You could imagine making a separate function for like compiling a constructor, and another function for compiling a function, another function for compiling a method, right? You could do it that way. I think it's nice, like there's going to be a lot of stuff that's shared, even though there's some stuff that's different. So it might be nice to think about, what part of that code can be shared, and can you just have like some conditions that say, well, if it's a constructor, then I'll do this special thing first, and then I'll do the generic part. Because obviously, once you get to the parameter list and the subroutine body, like that stuff is going to be dealt with pretty much the same way no matter what it is. Yeah, let's see. Is there anything else? I don't think so. I think that's pretty much. Yeah, I think we've gone over the majority of the syntax. I mean, there's a few things that I haven't put in here, like I don't think I put do statement in here, but we know what that is. We've gone over all the interesting parts, I think. So let's go back to this. Let's think about. So let's think about what code we need to generate for these things. So first of all, actually let's just do this. So when I see these two things, I see these two class var declarations, right? And they're both fields. We'll talk about static a little later. Let's talk about fields at first. So again, I don't need to generate any code for these, right? They don't correspond to actual code, but we do need to remember the fact that they exist And so when we refer to them later, we know what they are. These, right, so going back to the symbol table, if you recall, we talked about the symbol table having like,
Bless you.
there's really kind of two symbol tables, this global one and a local one. And the local one is going to be reset with every function or method that we compile, right? The global one is going to be reset for every class we compile. So the global one, static and field variables really correspond to an entire class, right? Those fields can be used anywhere through the whole class. So I'll just write this here, reset every time we compile a new class. And of course, since Jack requires having one class per file, that really means the same as per file. So depending on how you set this up, I mean, if you maybe it's as simple as for every, if you look at a directory and you loop through all the files, and you're going to call some function to compile each file, and maybe when you call that function, it just like creates a brand new symbol table. You don't actually have to worry about resetting it. It's just going to automatically be fresh every time you start compiling a new file. The more interesting thing is the fact that you have this local one, and every function you compile, you're going to have to reset it, at the beginning of that function. Right, these just go in the symbol table, as fields. So we remember the fact that they're fields. Something that I don't think I mentioned that's important is that, how the symbol table has this index, right? Because like, I have 3 local variables, I need to know this is local variable 0, 1, 2, right? It's really important that those indices are, like there's different indices for each different kind of variable, right? So what you can't do is have a single global counter for the whole symbol table, and every time you put a new variable in it, just increment it and say, oh, this is local 0, then this is argument 1, and this is like static 2, field 3. That's not going to work, because those indices, we use them to know like where to find the things in memory. So it's like, okay, the local variables are stored here, and so I need to know 0, 1, 2, how far do I have to go to find those things. So you're going to need to have one counter per kind of variable. So let me just write that here. I'll say index per variable kind. So e.g. there's local 0, 1, 2, and field 0, 1, 2, etc. Okay, does that make sense? Yeah, Zach.
For static variables, if you reset every time you make a new class, and then you have 2 classes that are calling the same argument, that they're both like
the same
static
name?
0, yeah.
Yeah, we'll talk about that later. It turns out that's okay because of the way that the assembler, when it sees a static variable, it like prefixes the name of it calls it like, name of the file dot, whatever.
And assigns it its own location.
Yeah, and so, right, and then it ends up getting its own, not the assembler, excuse me, the VM translator. The translator from VM code, it takes a bunch of separate VM files, and each time it sees a static variable, it's like, oh, you came from file foo.vm, so I'm going to name you, at foo.x or whatever. And then the assembler will see those, and it's like, oh, it just assigns a unique location. We'll talk about static variables in a little bit, but yeah, I mean, you're right to worry about that a little bit, but it turns out it works out okay. Okay. So we put those in the symbol table. Where? No. Okay. Fine. Let's move on. Let's talk about this constructor. Okay. So how are we going to generate code for constructor? So we're gonna say, of course, we'll say, you know, like function square game dot new. It doesn't have any local variables. That part works the same as any other function that we've compiled before. We would first look to see if it has any local variable declarations. This one doesn't have any, so fine. Now, before we start compiling the rest of the code, there are some things that we have to do. So the constructor's job, right, is to create a new object. Okay? What is an object really? It's really just an area of memory that's going to store the fields that belong to that object. Right? That's really all an object is. It's just like, it's an array of field variables. The methods, like, they don't need to be stored with the object. They're just code that we can run on an object. But so the first thing it needs to do is it needs to request some memory from the operating system. It says, hey, operating system, please go find me a chunk of memory of the right size. And once you've done that, you know, the operating system will, like, you know, mark that memory, says, okay, I found some free memory. I'm going to mark that it's being used, and then tell you the address of it. And now that's yours to use, and you can do whatever you want with that, you know, that piece of memory until you're done with it. We will talk about how that part works next week, but for now we just assume the operating system does that somehow. So we're going to allocate memory for the new object. And here's how we do that. We say call, well, okay, no, first we have to push, so there's a function called memory.alloc that allocates space, and we have to give it an argument, which is, you know, how much space we want. How do we know how much space we want?
How many keys in our symbol table?
Right, it's how many fields there are, right? So we say push constant 2, so 2 equals the number of fields. And then we say call memory.alloc 1, there's one argument. Okay? And then that's going to leave on the stack the address in memory where it's allocated us, you know, 2 words of memory that we can use to store this object. So what are we going to do with that address? We need to put it somewhere. Well, that's exactly what this is for. So we've already talked about that. We use that to reference arrays. This is used to reference objects. So this will always be pointing to the location of kind of the current object in memory. So if I want, you know, if I want to access the square field, I can just say, you know, this 0. And if I want to access the direction field, I can say this 1, which just means go to the this segment, wherever that is right now, and you know, 0 and 1 are the two fields there. Okay. So I will say pop, and I want to set this, so I do that by saying pop pointer 0. So we set this to the address of the newly allocated object. Okay, so now this 0 equals the square field, and this 1 equals the direction field. Right, and of course when we added square and direction to our symbol table, you know, we recorded the fact that square was index 0 and direction was index 1, so when we look those up later, we'll be able to know what to use. Okay. All right, let's see. So actually this, I don't think there's really anything, well, there's something a little interesting with this, right? To translate this code here, well, first of all, we just call square.new, and there's nothing fancy about that, because this is just calling a function of the square class, right? So we say, you know, push constant 0, we do that twice, and then we say push constant 30, and then we say call square.new 3, and then we're going to take the return value and put it in square, and we look up square and we say, square is a field, it has index 1, so I'm going to say, I'm going to pop from the stack and store that into this 0. So this is saying call square.new and store result in square, which is equal to this dot 0. An interesting point is that, like, well, I guess square.new isn't actually going to, because it's just a function in the square class, so it's, well, but it is creating a new object, right? So it's going to, like, it's going to set this to something else. So isn't that a problem that when I call square.new, it's going to set this to point to that new square object, right? Even though I had this pointing to something else. Is that a problem? Do we need to worry about, like, setting it back? This is like a pop quiz or something. Why are you shaking your head, Daniel?
Your nonchalance.
Because I'm too nonchalant about it. I'm like, is this a problem? You're right, it's not a problem, but why not? So it is. So honestly, like, I'm being serious. It is true that when we call square.new, it will set this to something else. It will set this to point to that square object instead of to this square game object that we were just allocating. Why is it okay for me to not worry about that? Sammy?
The VM translator changes the memory notation of this.
Right. Yeah, if you think way back to the way the VM translator worked, whenever we do a VM function call, it saves the values of this and local and argument and all those things on the stack and does the function call, and then when we return, it restores all of them, right? So that's kind of handled automatically. So that's really nice. We don't have to worry about that. When I set this to something, I can call whatever functions I want. I don't have to worry about it changing. That's all handled for me at a lower level.
Thanks, VM translator.
Yeah, exactly. Thanks, VM translator. Good job. Okay. I'll just put a note about that. Note, we don't have to worry about call to square.new clobbering this because the VM function calls save and restore it. Okay. Cool. Let's see. Next line of code is let direction equal 0. That's easy. We just push constant 0. Pop. Well, direction is this 1. And then when we say return this, that's how do I get the value of this to put on the stack to return?
Pointer 0?
Yeah, so I can say pointer 0. I can just say push pointer 0, push value of this, and then return. That's it. Okay. What's next? That part. Talked about that. Okay. So that's how we do a constructor. Let's talk about dispose. We're not going to translate the entire class, but okay. So this is a method, which means it looks like it has no arguments, but secretly it does, right? Secretly it's getting the address of the object on which this method should work as an argument. Okay, so say since this is a method, it secretly has one argument. Or, you know, every time you have a method, secretly there will be a first argument that is the address of the object. And right, this is where you can imagine, okay, if I have a generic function to compile a subroutine, you could just have an if that says, well, if it's a method, then I'm first going to do this thing to handle that one first argument. And then I can, after that, I can do the generic code that'll handle whatever the other arguments are. And that part will work the same way. So I want to say something like, well, what should I do? What should I do to, what should I do with that first argument? I mean, it's stored in argument 0, right? So what do you think I might want to do with that before I do the rest of the function?
Push it on the stack?
Push it on the stack. Yes, I need to push it on the stack if I'm going to do anything with it, but then there's somewhere else that I need to put it.
Temp?
Temp, no,
Oh.
not temp. Let's see, so I'll push it on the stack, push argument 0, and we're going to pop
Oh.
We're going to set this. Every time we're ever doing anything where we have, you know, that's like a method or a constructor, anything where we have like an object that we're working with, we're always, the very first thing we're going to do is take the address of that object and put it into this. Because from then on, anything that we want to do, you know, accessing fields of that object, calling methods on that object, anything, we have the address of that object in this. So, save the argument into this. Okay. You know, and then like, you know, here we would process. I guess actually we don't really need to do anything to process, even if there's more arguments. We don't need to process them in any way. Now, one thing we do have to be careful of, right? So when I'm reading in, you know, let's say this did have some arguments here, right? Normally, when I see some arguments, I start putting them in the symbol table. I say, oh, the first argument is called x, cool. You go in the symbol table, you have index 0, and you have type int, whatever. Your next is y, cool. You have index 1. But if I have a method, I have to be a little careful. I have to like set the counter to 1 to start, because 0 is already taken by that secret first argument. And then if I see an argument here that's like x, I'm like, okay, you actually have index 1. And then the next one has index 2, and so on. Yeah.
So, do we need to worry about this being an explicit argument or just an implicit argument?
What do you mean?
Like, is there, like, Python self?
No.
Okay.
Jack doesn't have that. Yeah, it's always implicit. Yeah. Yeah. So if you had an argument called self, that would be a different. That wouldn't be this argument. That would be a different one. So note with a method, we have to start numbering arguments in the symbol table from 1. Okay, so for example, you could literally, maybe we'll actually write some pseudocode for this. You could literally say, all right, if I'm doing a method, you know, as soon as you see the keyword method, right, you could say, all right, before I even get any further, let's output this code, we'll emit this code, and then we'll set the counter in the symbol table to 1 for arguments instead of 0. And then I can continue on normally, right? And then it doesn't matter. Then I'll parsing, you know, this, the name of it, and the type, and the arguments. And that'll all work fine. Okay, and then so how do we do this? Again, we're going to look up. We're going to say square.dispose. What is square? That's a variable. So this is an object. I'm calling a method on an object. So I'm going to first push square onto the stack. What is square? Yeah, what is square?
This
This 0? Yeah, I think it's a field, right? So, yep. So we'll say push this 0, and we're going to then call, I believe what the type of square is capital S square. So we'll say call square.dispose 1. And then do memory.deallocate this. So here we're going to push, this is just a function we're calling, so we don't have to push an object on the stack first. But we do have to push, you know, this argument, which is this. So we'll say push pointer 0, call memory.deallocate 1. And then to return, we have to say, you know, push constant 0. Return. Okay. So actually, yeah, let's do that. Let's go look at. Yeah, so let's actually, we already have a compile subroutine pseudocode, so let's think about how this is going to change. Okay, I guess what I said earlier doesn't quite work, because I said, oh, as soon as we see that it's a method, let's immediately emit the code that says, like, you know, put the thing in this. We can't do that because we first have to emit the thing that says it's a function. Did I put that over here? Or did I forget that part? I put that here. Maybe I forgot it over here. Yeah, I have to say function square game dot dispose 0. Okay. Yes, going back here. Okay. We need to say function whatever before we can start putting code for the function, and we need to know how many local variables there are before we can say function. So we have to at least read through the local variables before we can start doing that. But that's okay. So the first thing that we need to do, once we read the subroutine type, we can say, you know, if it's a method, if subroutine type is method, then we're going to increment the symbol table field index, or let's see, index for fields. Right? And then as we read in the, no, not for fields, excuse me, for arguments. Yeah. As we read in these parameters, we'll start assigning them indices in the symbol table, but they'll start at 1. I'll say and insert symbol table. Okay, and then down here, right, before we start compiling the statements, if it's a method, we need to emit, we need to say push argument 0. I don't need to say f. And I emit the code pop pointer 0. Easy. That code is actually just, it always looks exactly like that. Okay, and what about for constructors? Where should we add some, we need to also check if the type of, if it's a constructor, there's other special things we need to do. So I guess, I mean, we can really do it right here. Because this is just like, is there any special setup code that you need? All right, the thing that's different about methods and constructors is that they just need this little special setup code to set this properly. Right, and methods just get it as an argument. Constructors have to ask the operating system to allocate some memory and then set this to that. But both of them have this special setup code. So we can just add an elif here. It's a constructor. Then we say, well, what we have to say, what do we do over here? We push a constant, which is the number of fields. We call memory.alloc, and then we pop into this, right? So we'll say push constant, num fields. We can ask the symbol table for the number of fields. And then we say call memory.alloc1. And then we can say pop. Okay. Any questions about that? All right, let's see. Right. So another thing we need to talk about is so I think this came up the other day. So notice here it says do move square. It doesn't say something dot move square, right? So it's possible to have a subroutine call like this that doesn't have a dot in it. The way that Jack does this, which is different than what Java does, you can only do that with method calls. A method call on the current object. So it's as if you said this dot move square, right? So I say Java doesn't do it this way because in Java actually, so Jack's distinction between functions and methods, Java calls it like static versus like static functions in Java are the same as functions in Jack. You just call them kind of on the class, not on a specific object. But in Java, if you just say, move square, it just looks up and it says, oh, is that a static thing? You can call anything in the current class. It doesn't matter if it's a method, it'll call it on this, and if it's a static method, it'll just call it. But in Jack, I think to keep things simpler, if you're calling a function, you have to say like keyboard.keypress. Even if you're calling a function in the same class, you would have to say, that. So if you see something that's just a variable, with some parentheses after it, then you know you're doing a method call. So how do we translate that? Oops. Method calls, or so function call without a dot is always a method call. Right, so how would we translate this? So for example, we just have move square. You say, all right, it has to be a function call. It has to be a method call, but we're doing it on, instead of being given some variable that we're going to call it on, we're just going to call it on this. Whatever this currently is, that's what we're going to do. So we need to call this. We need to call it, but we need to pass this as the first argument. Right, because it's a method, so it needs a first argument, which is going to tell it what object it should work on, and we're just going to pass it this. So just pass this as first argument. Say on current object. Okay, and how do we know what class to use when we call the function? Because we have to say, call class name dot whatever.
We have class name stored as a variable.
What was that?
We have it stored as a variable.
Yeah, so since it has to be on the current class, it's easy. It's just like you have the current class name stored in a variable somewhere. So it would translate to something like push pointer 0. So we'll put this on the stack, and then we'll call square game dot move square 1. Square game equals name of current class. Okay. Well, then of course we would say like pop temp 0 or something like that, because it's a void thing. Okay. So where would that, let's see, where would that go in our, do we actually have any code for that in our, yeah, we do right here. So here was some pseudocode that we wrote a while ago when we talked about how we're going to parse this. Because this does correspond to this kind of slightly difficult thing to parse, where if you see an identifier, you actually don't know yet what it's going to be. Basically, and we have like we kind of wrote as if there are two different functions for compiling a dotted subroutine call and a normal subroutine call. You could probably of course most of the code in those are going to be the same, right? So hopefully you can organize things such that maybe you even just like make one function to compile a subroutine call, but you just pass it like a Boolean that says whether you should see a dot or not, or something like that. There should be ways to not duplicate the code. So maybe it would be like Boolean says whether there is a dot, for example. Okay. fine. Okay, so there's really only one thing left to talk about, I think, which is let's look at let's just look at square really quick. Is there anything different in here to talk about? So it has some fields. Constructor takes some arguments. There's really nothing that's that different. Bunch of methods. Okay, so let's look at okay, actually there's a copy of this. Yeah. So this is the final test. So this is the final test both for your compiler. When you get your compiler to, you know, like you really have to get this uses every single feature of Jack. So you're not going to be able to compile this Pong game unless you've completely finished your compiler.
In other words, if I can completely compile Pong, I don't have to worry about compiling anything else.
Yeah, exactly. Indeed. If yeah, all those other tests you're doing along the way, worthless. You just have to do Pong. That's all. Very simple. But and it actually, you know, it actually doesn't use that many features beyond the square game. The main thing it does use is the static thing, which we'll talk about now. But yeah, this will be the last test you'll do. Once you can actually compile this and it, you know, then you run in the VM emulator. That's a very nice feeling when, like, you wrote this compiler, you compiled this code, and then it generates some VM code and you run it and you can play Pong. It's super cool. This will also be kind of the final test for if you do the operating system project 12. This also uses tons of operating system services, right? And so, you know, after you finish the compiler, it's a great feeling, but it's a little incomplete because, like, there's still a lot of code that someone else wrote that's you know, giving the operating system services that's kind of supporting it. Once you actually write that too, that's a really, you know, that's like, no, you completely wrote all the code that's making this work. Okay, so how does this static thing work? And actually, the way that Pong game uses it is interesting in its own right. It's an interesting object-oriented design pattern. So, what is a static field? A static field means it is a field that does not belong to particular objects. It just belongs to the class as a whole. So, you know, this bat field, if I made multiple Pong game objects, there would be, each of those Pong game objects would have its own copy of that bat field, and they could all be different, right? This, however, this static Pong game, you could call it a static field. There's only one that's shared among all Pong game objects. So they can all refer to it, but there's only one of them. Why would you want this? There's a few reasons. And Java has this too, and it uses the same keyword, static. So you can say, you can make a static field and it'll be shared among all objects of that class. It's not like super common, but you know, for example, maybe like you have a whole bunch of objects that represent some kind of data, but they all need access to a certain database, right? And so you can make like a database connection object and just have it be static, and so they all are referencing that same thing. I don't know if it's a great example or not, but just imagine something where you kind of want all the objects to share something and all be able to access the same thing. The way it's used here is interesting. So this is called the singleton pattern. And so it looks a little odd. It's like the Pong game class contains a static field which contains a Pong game. Like, is that recursive? It's not exactly recursive. So there's a single Pong game field. The idea is there will only ever be a single Pong game object. Ever. And the nice thing about this is, you know, so there's a constructor, of course, and you could call the constructor multiple times to make multiple Pong game objects, but that's not what you're intended to do. You're not actually intended to call the constructor directly. You're intended to call, first of all, call new instance. So new instance is a function, so it's not a method. You just say, you know, ponggame.newInstance. And it actually calls the constructor and, you know, creates a new Pong game object, and it stores it in this static field instance. Then you can call this function getInstance. Again, this is a function, not a method. You can just say ponggame.getInstance, and it will return you that one Pong game object. Why would you want to do this? Well, the nice thing about doing this is that if you're going to have a big code base and like all the code through the whole code base is all going to need to refer to that Pong game object, it's kind of like a principled way to make a global variable. Because you don't have to pass that Pong game object around as a parameter everywhere. Anywhere that you want to access it, you just say ponggame.getInstance. Right? And that's a function. You can call it on that class, and it'll just say, oh yeah, I've got this one object that's stored in the static field, and I will give you a reference to it. So that is definitely an interesting use of the static field ability. And you will see this used for things like, for example, a database connection. If you've got a big code base and all the code base is dealing with like talking to some database, you might have a class that kind of encapsulates your connection to the database, and you use the singleton pattern where you say, you know, there's just going to be one instance of this class that's going to set up a connection to the database and allow you to talk to the database. But instead of passing that around as a parameter everywhere, right, because like basically every single function in your entire code would have to have that as a parameter, you just say, no, I'll just make a static method that allows you to, you know, anywhere you want, you can request the database connection object and then use it to talk to the database. All right, so how is this going to work? Well, somehow we have to, all these, you know, so all these fields are going to be stored when you create an object. You'll allocate some memory for them, and then they'll be stored there, right? But this has to be stored somewhere else, right? We can't, we definitely can't store it in objects because number one, we may or may not actually create any objects of this class. And number two, there's only supposed to be one. We shouldn't have multiple ones, you know, per object. So this is where we cheat a little bit, because from the ground up, like starting with the way the assembler works, things were carefully designed so that this kind of works out nicely, right? So the assembler, when it sees a variable name, it just automatically assigns it an address, right, starting at 16, if you remember that. Really the only time we use that is for static fields. So if we just say, right, so in the virtual machine there's this so-called static segment, and when we say, you know, some static variable, when that gets translated to assembly, it's going to translate it into, you know, the name of the class .3 or something, whatever it is, and it'll just basically every static thing for each class will end up getting its own unique location, you know, starting at 16. So how do we actually do this? Well, oh, they spelled singleton wrong. So when we see this, right, we'll make a symbol table entry. You know, something like instance is a home game static 0. Right, so again, we have an index counter also for static things. And we can do this per class. It's okay that this gets wiped out every time we compile the next class. And I think Zach was asking about this earlier. Because when we refer to stuff in the static segment, when the VM translator translates that, it's going to say, oh, I'm going to make sure to prefix the name of this file to it to make sure it's unique among other, among other files. So that is already taken care of. And when instance is used, so for example, well, actually, let's go ahead and get instance. So for example, how would we translate this function? Well, we would say, all right, function onGame.getInstance 0. And we need to push that instance variable on the stack. So we would say, instance, let's look that up in the symbol table. That's a static thing, it has index 0. So actually, literally, all we have to say is push static 0 and then return. So there's actually not much we have to do here. It's really not actually that hard. The important point is, that this gets translated by the VM translator into, something like, at ponggame.0, gosh, I'm already forgetting the assembly. And then, we'll have code to push that on the stack, etc. Doesn't matter. The point is, when it sees this push static 0, it translates it into this, and then the assembler will assign a unique location, in the range 16 to this variable. Okay, so that's kind of why this all works. You can imagine a different way of setting this up so that we don't have special support for this in the assembler or the VM translator, where we would have to actually generate some code to allocate some memory to store the static variables and make sure that we keep track of where they are and stuff like that. But we kind of, in this case, we kind of put it all off to the assembler and just say, yeah, just figure out where we should put these and just make sure they're unique. So. All right, questions about any of that? One thing I think I forgot to mention, go back to and it's not that big of a deal, you probably could figure this out, but when we say return this, you might wonder how we know what this represents. So it's not a variable. It won't be in the symbol table. You could imagine doing things that way. Maybe you have a special entry for it in the symbol table or something. But actually what the grammar specifies is this. There's these four, like, what it calls keyword constants. So true, false, null, and this. So those can't be used as variable names. They're special keywords that have some special meaning. So it's actually really easy, right? Every time that if you see an expression and it happens to be the keyword this, you just use pointer 0. You just push pointer 0 and that's it. That's how you translate this. The only time, and you can't say let this equal something. That's actually not even allowed syntax, right? So you would never do that. The only time you're going to pop to pointer 0 is in one of these special times where you're like, like here, where you're setting up a method call or a constructor or something. So let me write this down. This is a keyword constant, which is always compiled to push pointer 0. All right. So I think that is pretty much it for the compiler. If you have any other questions, or feel free to ask. If you need help debugging, feel free to ask. This is probably the only thing I think that might be harder to debug than the compiler is when you write the operating system code to do the memory allocation. I struggled with that for a while, but I'm happy to help debug. And maybe, we'll see, maybe I'll think about this. I might start Tuesday with like an example of here's how I might go about, maybe I'll like make an incorrect compiler on purpose and see if we can like debug it, just to see like here's how I might go about debugging my compiler, because it's tricky. Simon?
So what value is null?
Null is 0.
So it's the same as false?
It is the same as false, yes. Yeah. I mean, like, kind of semantically, they kind of represent different things, but they're actually, yeah. I mean, in Jack, you could say, if something, return true, else return null. Like, it would work. It would be weird, but, yeah. All right.